Hello everyone, very good evening. Kindly confirm if audio video is clear. Good evening everyone. Please confirm if audio video is clear. Okay, all set. Thank you very much. Okay guys, so welcome back to the 10th lecture of Discrete Mathematics, in which we are discussing set theory and algebra. So let's have a quick revision that what did we discuss in the last class. So in the last class we tried to understand the concept of one-one function, that what actually a one-one function is and how many one-one functions are possible from set A to set B, and when exactly one-one functions are possible. Apart from that, we discussed about onto function, that what actually an onto function is, when exactly an onto function is possible from set A to set B, and how many onto functions are possible from set A to set B. Now we have also understood the different cases related to number of onto functions, that how many onto functions are possible. Then a bijective function is nothing but a function which is injective as well as surjective, that is a function is both one and onto, it will be called a bijective function. If function is a bijective function, then inverse function is possible for that function, and we also learned that how we can calculate or how we can obtain the inverse function for a given function provided our function is bijective. Okay, so what are we going to discuss in the today's session? So today's session is related to concept of group theory. So in this session, we are going to introduce the concept of group theory. So we'll try to understand what actually an algebraic structure is, what is a semigroup, what do we mean by monoid, what do we mean by group, and what do we mean by Abelian group. And we will also try to solve some questions related to these concepts. Okay, so let's start with the very first definition, that is algebraic structure. So what actually is an algebraic structure? So the idea is you should have a non-empty set S. So a non-empty set S, it should a non-empty set S with respect to, so there will be a set and binary operation with respect to, sorry, with respect to binary operation asterisk. So it can be any binary operation with respect to binary operation asterisk is called an algebraic structure. Simple definitions, only 5 definitions we need to understand, and based on that we will try to solve some questions. This is called algebraic structure if for any two elements A and B belonging to set S, if you take any two elements A and B from set S, and if you perform the binary operation asterisk on those two elements, then the result, that is A asterisk B, should also belong to set S. So what did we say? The set S with respect to binary operation asterisk will be called an algebraic structure if for any two elements, for every two elements A and B belonging to set S, if you perform the binary operation asterisk, then the result should also be present in the set S. It means your set S must be closed with respect to binary operation asterisk. That is, you should not have to include any other element in set S such that the binary of the property is not satisfied. So the idea is that the set S should be closed. Anyway, we'll take the examples from for each one of them. So this is called closure property. So let me just give you a quick understanding the idea. So first of all, I don't know whether there are so many. So this is set of natural numbers with respect to binary operation addition. This is set of natural numbers with respect to binary operation multiplication. This is the set of natural number with respect to binary operation. I don't know whether you are able to them all or not. So set of natural numbers with respect to division. Set of all integers with respect to addition. Set of all integers with respect to multiplication. Set of all integers with respect to set of all integers with respect to set of all rational numbers with respect to addition. So Q is representing set of all rational numbers. Set of all rational numbers with set of all rational numbers with respect to set of all rational numbers with respect to. Now 0 is also a rational number. 0 is also a rational number. We are saying set of all non-zero. This asterisk is trying to represent set of all non-zero rational numbers. This no rational number, set of all rational numbers. And this Q asterisk is set of all non-zero rational numbers. So that is we are not including 0 in this set. Okay. So set of all non-zero rational numbers with respect to addition. Set of all non-zero rational numbers with respect to multiplication. Set of all non-zero rational numbers with respect to and set of all non-zero rational numbers with respect to division. So let's try to understand the meaning of algebraic structure. So if I take any two natural numbers and if I perform the addition, result will also be in the set of natural numbers. Yes, sir. If I add any two natural numbers, result will also be a natural number. So yes, set of all natural numbers with respect to addition is algebraic structure. It is closed. Now, if I take any two natural numbers, if I multiply them, result will also be a natural number. So this is also closed. If I take two natural numbers, if I perform the subtraction operation, is it necessary that result will also be a natural number? No, sir. Sir, if I simply write 2 minus 5, then this is equals to minus 3, which does not belong to set of natural number. That means if you take two numbers and if you perform the binary operation, subtraction on those two numbers, then the result need not be a natural number. Therefore, this set of natural numbers with respect to binary operation minus is not closed. That's what the closure property actually means. Okay. Now, fast cover everything. So, set of all natural numbers with respect to division? No, sir. Obviously, not closed. Set of all integers with respect to addition will be closed. Set of all integers with respect to multiplication will be closed. If you subtract any two integers, result will also be integer. It contains both positive as well as negative integers. So yes, it is also closed. So division is not closed. 2 divided by 5, not in 2 divided by 5, not an integer. Now, if I take any two rational numbers, if I add them, result will also be a rational number. Yes, sir. If I take any two rational numbers, if I multiply them, result will also be a rational number. If I take any two rational numbers, if I subtract them, the result will also be a natural number. Oh, sorry, result will also be a rational number. Yeah, so this is also correct. Now, the idea is, sir, set of all rational numbers with respect to division is closed or not? Sir, the important thing is that 0 also belong to set of all rational numbers. So if I divide a rational number a by 0, it does not belong to set of all rational numbers because it is not defined. So because of the 0, this set of all rational number is not closed with respect to division. I hope you understand. It's already gone. Now what? So set of all non-zero rational numbers. Okay. Set of all non-zero rational. Take any two non-zero rational number, result will also be non-zero rational number. Take any two non-zero rational numbers, multiply them, result will also be a non-zero rational number. Take any two non-zero rational number, subtract them. Will it be closed? No, sir. Why? If you take one rational number p by q, so we are saying all rational numbers. So there will be, if I perform p by q minus p by q, it will be 0, which does not belong to set of all non-zero rational numbers. I have said 0 is not present in the set. So p by q minus p by q will be 0, which is not present in the set. Therefore, it is not closed. Sir, if I take any two non-zero rational numbers, then the division will be applicable. And if I have p by q and one rational number, another rational number is r by s, if I divide them, I'll get ps by rq. It will also be a rational number. Yes, sir. So, and it will also be non-zero rational number. So, the idea is that set of all non-zero rational number with respect to division will be closed, but set of all rational number with respect to division will not be closed because of the presence of zero. Clear? Anyway, so I hope you have understood the concept of algebraic structure. Now let's move to the other definition, and I'll fill the remaining table after we have discussed all the types of properties. So what's the first thing? There are non-empty set S with respect to binary operation asterisk is called an algebraic structure if the set of elements are closed with respect to binary operation asterisk. You don't have to include any other element apart from the elements of the set. Now, so what is our semigroup? So the very first thing which is necessary for something to become a semigroup is that it must be closed. That means your set with respect to binary operation asterisk must be an algebraic structure. So how do we start defining the concept of semigroup? An algebraic structure. So before becoming a semigroup, it must be an algebraic structure. So an algebraic structure what? Sir, S comma asterisk. That is, if we are saying S comma asterisk is an algebraic structure, what does it mean? It means that set of elements of set S with respect to binary operation asterisk are closed. So that's the first property. So an algebraic structure S comma asterisk is called a semigroup. Called a semigroup if A asterisk B asterisk C is equals to A asterisk B asterisk C for all A, B and C belonging to set S. That means for a set S with respect to binary operation asterisk to be called a semigroup, it must be closed because it is an algebraic structure. Apart from that, the binary operation asterisk must be associative. That is, associativity property must be satisfied by binary operation asterisk. Now, please try to understand. An operation is either associative or not associative. It has nothing to do with the type of elements. It has nothing to do with the type of elements. Either an operation will be associative or it will not be associative. It does not change with the type of elements present in the set. Now, someone may say, sir, real numbers, if we talk about multiplication, then multiplication of real number is associative. But what about multiplication of matrices, whether it is associative or not? So some people may say that, sir, multiplication of matrices is not associative, but it's not so. Multiplication is associative. So multiplication of real number or multiplication of matrices, whatever you call, it will remain associative provided the multiplication is defined. If a multiplication is defined, then the multiplication operation will remain associative. As long as operation is defined, it will remain associative if it is associative, or whatever the type of element are. Okay? So that's the idea. So what does it mean, sir? We can simply say, if we talk about algebraic structure, then the only property that must be satisfied is closure property. For a semigroup, two properties are required. First one is closure property. Second one is associative property. If both the properties holds true, then the set with respect to binary operation will be called a semigroup. Next one is monoid. So just like before becoming a semigroup, the set with respect to binary operation asterisk must be closed. That is, it should be an algebraic structure. Similarly, before becoming a monoid, your set with respect to binary operation asterisk must be a semigroup. So the definition will start like this. A semigroup, so first of all, it should be a semigroup. So the moment you said it should be a semigroup, we have said two different things. That it should be closed, it should be associative. Otherwise, it cannot be a semigroup. If it is not a semigroup, it cannot be a monoid. So these two properties are definitely necessary properties for something to become a monoid. So a semigroup S comma asterisk is called a monoid if there exists an element E belonging to set S such that there should exist an element E in the set S such that if you perform the binary operation of E with any element A, any order, so E asterisk A or A asterisk E, it should be equals to A for all A belonging to S. Come on, what are we saying? In the set there should be an element E such that if you perform the binary operation of any element A with that element E, then the result should be A only, and such element E is called identity element. E is called identity element with respect to binary operation asterisk whatever the binary operation. Now please try to understand, we already know, sir, if the operation is addition, what will be the identity element? Sir, if you have any element A, if you add 0 with that, you will get A only. Therefore, 0 is the identity element with respect to addition. With whatever element, if you add 0, result will be that element A only. Therefore, the identity element with respect to addition will be 0. Similarly, what will be the identity element with respect to multiplication? Sir, if you multiply any number by 1, if you multiply any number x by 1, result will be x only. So a plus 0 will be a for all a belonging to real numbers. X dot 1 will be equals to x for all a belonging to real numbers. So what can we say? Identity with respect to addition is 0. And identity with respect to multiplication is 1. So identity element will depend on the operation as well as on the type of elements, right? So if it is a matrix, then the identity will eventually become identity unit matrix, identity matrix, known as identity matrix. So similarly, if addition of matrices is performed, then identity element will become a zero matrix. So that's the idea. So semigroup, sir, what is the property? Sir, and semigroup will be called a monoid. A semigroup will be called a monoid if identity element with respect to binary operation asterisk is present in the set. So the third thing that must be satisfied by a monoid is identity element present present. Okay, so if you have reached up to monoid, then the next definition will be the definition of the group. So before becoming a group, your set with respect to binary operation must be a monoid. So the idea is a monoid S comma asterisk. So the moment we are saying monoid, three properties are already satisfied: closure property, associativity property, and identity property. A monoid S comma asterisk is called a group if for each element A belonging to set S, for each element A belonging to set S, there exists an element B in the set S such that for each element A belonging to set S, there exists an element B belonging to set such that A asterisk B is actually equals to B asterisk A equals to E. And this E is nothing but identity. Sir, is it necessary that identity element will be present? Yes, sir, it is already a monoid. So we know that identity element is present in the set. So A asterisk B should be equals to B asterisk A and it should be equals to E, that is known as identity. So that means what is the notation for A and B? So the idea is, sir, if A asterisk B equals to B asterisk A equals to identity element, then A and B are called inverse of each other. A, element A, and if A asterisk B is equals to E, then A and B are called inverse of each other. Are called inverse of each other. So what did we say? Sir, for each element A, there should be an element B such that A asterisk B equals to identity element. That means for every element of the set, the inverse of that element should also be present in the set. For every element of the set, inverse, which is B, should also be present in the set. So four properties must be satisfied in our group. First one is closure. Second one is associative. Third one is the identity. And what is fourth one? Inverse of every element should be present in the set itself. Inverse of every element of the set must be present. The set must be present. Okay, so if this four properties are satisfied for the elements of set S with respect to binary operation asterisk, then the set with respect to binary operation asterisk will be called a group. The last one is an abelian group. So when do we say that a set with respect to binary operation asterisk is an abelian group? Okay, anyway, we are saying abelian group, that means we already know that it is a group. So a group S comma asterisk, that means four properties are already satisfied by the elements of set with respect to binary operation asterisk. A group S comma asterisk is called an abelian group, or commutative group. So another name for abelian group is commutative group or commutative group if a group is called a commutative group if A asterisk B is equals to B asterisk A for all A and B belonging to set S. What does it mean? That is, binary operation asterisk must be commutative on the elements of set S. Elements of set S. So that's what you need to understand. See, associativity property depends only on the operation. associativity property depends only on the operation, whereas commutative property depends on the operation as well as on the type of elements on which the operation is being performed. Clear? So let's see, if you multiply two real numbers, then it will be commutative, but multiplication of two matrices is not commutative, because if A dot B exists, then we know that B dot A will also exist, but they need not be equal. That is, the multiplication of matrices need not be commutative. Yeah? So when do we say that a set with respect to binary operation asterisk is an abelian group? When five properties are satisfied. What are they? So closure property is satisfied. Another, associative property is satisfied. Third, identity property is satisfied. Fourth, inverse is present for every element of the set. 5, commutative. So if these 5 properties are satisfied for the elements of set S with respect to binary operation asterisk, then it will be called an abelian group. Anyway, so let's try to understand that what happened here. Please look at this. So set of natural number is closed. Yes. Set of natural number with respect to multiplication is also closed. Set of natural number with respect to subtraction is not. Set of natural number with respect to division is not closed. Set of integer with respect to addition is closed. Set of integers with respect to multiplication is closed. Set of integer with respect to subtraction is closed. Set of integers with respect to division is not closed. Set of all rational number with respect to addition is closed. Multiplication is closed. Subtraction is closed, but it is not closed with respect to division because of the presence of 0. Set of all non-zero rational number is closed with respect to addition, is closed with respect to multiplication, is closed with respect to subtraction. No, it is not closed with respect to subtraction, because the 0, p by q minus p by q will be 0, which does not belong to set of all positive non-zero rational numbers. Set of all non-zero rational numbers. So it is not closed, but set of all non-zero rational number with respect to division is closed. Now, something which is not an algebraic structure can never become a semigroup. So this sets with respect to binary operations which are not closed can never become semigroup. So we have already eliminated those from the consideration. Now let's try to understand. Addition is associative. Now let's talk about this. Sir, addition is associative. Yes, sir. Multiplication is associative. Yes, sir. Multiplication. Here also, addition is associative, sir. Multiplication is associative. Yes, sir. So subtraction is associative. No, sir. Subtraction is not associative. Subtraction is not associative. So let me use new color. That because of associativity property, set of all integers with respect to subtraction will not remain a semigroup, though it is an algebraic structure, because set of all integer is closed with respect to subtraction, but subtraction is not associative, therefore it is not a semigroup. Okay, so set of addition is associative. Addition, multiplication is associative. Subtraction is again not associative. Okay, sir. Sir, addition is associative. Multiplication. Sir, division is not associative, sir. Division is not associative. Yeah. So I hope you understand. 1 divided by 2. If I write like this, sir, 8 divided by 2 divided by 4, then you know what will be the value. So this is 8 divided by 2, 4 divided by 4 will be 1. But if I write it like 8 divided by 2 divided by 4, so 2 divided by 4 will be 0. And I mean, it will be absurd. It will be 16 even if you consider fractional or real numbers. Not associated. Now, let's move ahead. Sir, these structures which are not semigroup can never become monoid. So, let's first remove those observation. Now, let's talk about monoid. Sir, set of natural number is a monoid with respect to addition or not? Sir, the identity element with respect to addition will be 0, and 0 does not belong to set of natural numbers. Therefore, it is not a monoid. It is not a monoid. Clear? Sir, with respect to multiplication, sir, 1 belongs to, with respect to 1, with respect to multiplication, identity will be 1, and 1 belongs to set of natural number, therefore, yes, set of natural numbers with respect to multiplication is a monoid. Now, next one, sir, set of integers, sir, in set of integers, 0, so 0, 0, 0 is the identity, and 0 belongs to set of all integers, therefore, also a monoid. Sir, 1 belongs to set of integers. 1 belongs to set of integers. Therefore, set of all integers with respect to multiplication is a monoid. Sir, here 0 is obviously present. 0 belongs to set of all. 0 belongs to set of all rational numbers. Therefore, identity is present. 1 belong to set of all rational numbers, and therefore identity with respect to multiplication is also present. So both of them are. So what about this? Sir, identity with respect to addition is 0. Identity with respect to addition is 0, and 0 does not belong to set of all. So does not belong to set of all non-zero rational numbers. We are already saying it is non-zero rational numbers. Therefore, it cannot be a monoid. Apart from that, sir, 1 belongs to set of all non-zero rational. 1 belongs to set of all non-rational. Therefore, set of all rational numbers with respect to multiplication is a monoid. Clear as of now? बिल्कुल बिल्कुल लेके रख लो, है ना? इंटरेस्टेड तो आप हो नहीं चीजों को समझने में, जब क्वेश्चन आएंगे तब देख लेंगे. चलो सर, तो ये सारी की सारी कहानी हो गई. अब बात करते हैं सर ग्रुप की. व्हाट अबाउट ग्रुप? सर, ग्रुप के लिए इनवर्स होना जरूरी है. सो लेट्स ट्राई टू अंडरस्टैंड. If we are interested in the group, then inverse should be present for every element of the set within the set itself. So anyway, these sets which are not monoid with respect to binary operation can never become group. Now let's talk about remaining sets. Sir, with respect to set of all natural numbers and operation is multiplication. If we take 2, what will be the inverse of 2? Sir, inverse of 2 will be 1 by 2, because if we take 2, then with what number? If we take 2, then with what number we multiply 2 that the result comes out as 1, that is the identity element. Sir, so the question mark should be 1 by 2. But 1 by 2 does not belong to set of all natural numbers. Therefore, inverse will not exist. So please try to understand. Inverse will not exist for any element in this set except for the identity element, that is 1. So inverse of 1 will be 1. Inverse of 1 will be 1. But if you take 2, inverse will be 1 by 2, not present in the set of natural numbers. 3, 1 by 3 is not present in the set of natural numbers. Clear? So, this is not a set of natural number is not a group with respect to addition. Set of natural number is not a group with respect to multiplication. Natural number is not a group with respect to subtraction. Set of natural number is not a group with respect to division. Now, sir, if we take set of all integers, with respect to addition, for every positive integer there will exist a negative integer of equal magnitude. Therefore, for every element, if we take a, if we add with minus a, you will get 0, which is the identity element. Therefore, inverse will be present for every element of the set. Therefore, the set of all integers with respect to addition is a group. Sir, what about set of all integers with respect to multiplication? Again, sir, 0 belongs to the set. Now, please try to understand, it is not a group. You simply need to remember one thing. What? Sir, with what number we multiply 0 that the result comes out as 1? So, there is no number which if multiplied with 0 then produce the result as 1. That means that inverse of 0 can never exist with respect to multiplication. inverse of 0 can never exist with respect to multiplication. Down. Inverse of 0 can never exist with respect to multiplication. Inverse of 0 can never exist with respect to multiplication. Okay, go ahead. So if we take set of all rational numbers with respect to addition, then this is algebraic structure. So yes, and for every positive rational number, there will be a negative rational number of equal size. For every positive rational number, there will be a rational number of equal magnitude. Therefore, this will also be a group with respect to addition. Sir, what about multiplication? Sir, this is a monoid, but the problem is 0 belongs to. For every p by q, you will have q by p. For every p by q, you will have q by p, such that p by q multiplied by q by p will be equals to 1. But 0 is also present in this set of all rational numbers, and inverse of 0 can never exist with respect to multiplication. So 0 belongs to set of all rational numbers, therefore not a group. Therefore not a group, because the inverse of 0 can never exist with respect to multiplication. Sir, if we take the set of all non-zero rational number, then there is no 0. So for every p by q, you will have q by p. For every p by q, you will have q by p, such that p by q into q by p will be 1. That means inverse will exist for every element of the set. Therefore, it is also a group. So we started from so many sets along with different types of operation, but we realize that set of all integer with respect to addition will be a group, set of all rational numbers with respect to addition will be a group, and set of all non-zero rational numbers with respect to multiplication is a group. No other set with respect to any other binary operation is a group. Now, because we are talking about addition, multiplication, we are talking about addition and multiplication with respect to real numbers. So set of natural number is also real number. Set of integers will also belong to set of real numbers. Set of rational numbers will also belong to set of real numbers. And multiplication and addition of real number is commutative. Therefore, all these groups will also be abelian group. All these groups will also be abelian group or commutative group. Okay. So let's talk about some questions. Initially, very easy question. Talk about this. So A is a set which contains the elements 0 plus minus 2 plus minus 4 plus minus 6 etc. And B is a set that contains elements 0 plus minus 1 plus minus 3 plus minus 5. So basically set A is the set of all even integers, positive as well as negative, and set B along with 0, and set B is a set of all odd integers, positive as well as negative, along with 0. Now what is being asked, which of the following is not a semigroup? So when you think of semigroup, you will think of associativity. You will think of associativity, yes or no? But please try to understand. Here they are asking that set A with respect to addition is a semigroup or not. Set B with respect to addition is a semigroup or not. Set A with respect to multiplication is a semigroup or not. Set B with respect to multiplication is a semigroup or not. Now we know, sir, all of them are the real numbers, and addition and multiplication are associative. Addition and multiplication are associative. So does it mean that all this four set along with the operation are semigroup? No, sir. Because if you are interested to know whether a set with respect to binary operation is a semigroup or not, then two properties need to be checked. First one is closed or not. If closed, then we will talk about associativity. If closed, then only we will talk about associativity. Now, addition and multiplication are associative. Therefore, this is satisfied by all four options. But before we look for the second choice, that is associativity, first of all, it should be closed. So check whether these sets with respect to given binary operation are closed or not. So look at this. Sir, if you take any two even integer, if you perform the addition, the result will also be an even integer. Therefore, it is closed as well as associative. Is closed as well as associative. Therefore, it is a semigroup. Therefore, it is a semigroup. So if we take any two even integers, if we perform the multiplication, the result will also be an even integer. That means it is also closed. Multiplication is associative. Multiplication is associative. So it is associative as well. Okay, sir. Now, if we take two odd numbers, forget about 0. If you take two odd numbers, please look at this. Sir, 1 plus 3 is equals to 4, which does not belong to set B. Therefore, not closed. Therefore, set B is not closed. Not closed with respect to addition. Now, something which is not closed can never be a semigroup. Therefore, not a semigroup. So, that's what it is asking. That which of the following is not a semigroup? So, option C, the correct answer. Now, let's look at the option B. Sir, if you take any two odd integers, if you multiply them, the result will also be an odd integer. Therefore, it is closed as well as. Is it closed? Yes, sir, it is closed. Take any two odd integers or 0. If you multiply it with 0, result will be 0. Otherwise, if you take two odd numbers, if you multiply them, result will also be an odd number. Therefore, it is closed. Apart from that, multiplication is associative. Multiplication is associative. Okay. Option C is the only choice to given question. Now, let's talk about next question. You guys can 1 minute time and try to provide the answer. Read the question, think about it, and try to provide the answer. So basically, it will require some basic knowledge of theory of computation. So what basic knowledge is required? This asterisk represent the set of all strings over the alphabet. Here, the alphabet are 0 and 1. That means sigma asterisk represents the set of all binary strings of 0 and 1. Asterisk represents set of all binary strings of 0 and 1. Okay, thank you. So consider this sigma asterisk of all string over the alphabet 0 and 1. So sigma asterisk, that is the set of all, we are talking about set of all binary strings of 0 and 1 with respect to concatenate operation for a string will be what? So basically, let's say assume with respect to concatenation operation for a string will be what? So the idea is, sir, if we take any two binary string, and if we concatenate them, the result will also be a binary string of 0 and 1. Sir, what else will appear in the because of concatenation? Sir, what do we mean by concatenation? 1 0 1 1 0. Let's assume this is one string, and let's assume that I denote the concatenation using this symbol, whatever, or simply asterisk. Assume that asterisk represents the concatenation of two strings. So 1 1 0 1. Sir, what will be the result? Sir, because of concatenation, the second string will be appended after the first string. So the result will be 1 0 1 1 0 1 1 0 1. So that will be your result. So in the first string you have zeros and ones. In the second string also you have zeros and 1. So if you perform the concatenation, the result will be a string of 0 and 1 only. So what can we say? Sir, set of all binary string with respect to concatenation is closed. Set of all binary string with respect to concatenation is closed. Yes, sir. Is closed. Is it associative? Yes, sir. It will be associative as well. Let's assume 1 1 0. Concatenation with 1 0 1. Then 1 1 1. Now, will it be same as 1 1 0 concatenation with 1 0 1? Then concatenation. Yes, sir. The precedence will be given to the brackets first. So first of all, it will be evaluated. That means 1 1 0 1 0 1. will be finally concatenated with 111 and the result will be 110, 101, 111. Similarly, here first RHS will be evaluated, so 110 will remain as it is, and this will be concatenated with the result of this concatenation, that is 101, 111, and finally the result will be 110, and then we'll append the second argument, that is 101, 111 with this, and both of them are same. So we know that concatenation of binary string will be associative as well. Will it be associative? Yes, sir, it will be associative. Sir, do we have identity? So, sir, two properties are satisfied. It is closed, it is associative. Now, do we have identity element in the set of all strings? So, that's where the knowledge of TOC comes to the picture. That if you are taking the set of all binary strings of 0 and 1, then null string, that is epsilon, null string belongs to set of all binary strings of 2 and 1. So if you take any, assume 110, 11, if you concatenate it with epsilon, which is the null string, this is actually nothing. So it will come out as 1011 only. It will come out as 1011 only. So the idea is, do we have an identity element with respect to concatenation operation? Yes, sir, we have the identity element with respect to concatenation operation over these binary strings of 0 and 1. Therefore, this set of all strings of 0 and 1 with respect to concatenation is a monoid as well. Yes, sir, it is a monoid. Why? Sir, it is a monoid. Null string belongs to sigma string. Belongs to. Okay, sir. Third property is also set. So because it is closed, it is an algebraic structure. Because it is associative, it is a semigroup. Because it is a entity, I wanted identity, that is null string, belong to sigma string. And because identity is present, it is a monoid as well. Now, my question is, if you have a binary string, let's say assume 1101, right? With what binary string we should concatenate it? So 1101 should be concatenated with what binary string such that the result is the null string? Sir, because of concatenation of two binary strings, the string length will only increase, it cannot reduce. The length of the identity element, that is the length of the null string, is actually 0. There is a string of length 4 and the result which is required is of length 0. So because of concatenation, the string length will only increase or remain same. Sir, when exactly it will remain same? When we concatenate with epsilon, it will remain 1101 only, that is the string length will remain 4 only. So on concatenation, the string length will increase or will remain same, it can never reduce. That means inverse will not exist for any binary string except for epsilon. Inverse will not exist for any binary string except for epsilon. So, or null string. Inverse will not exist for any binary string except for null string. Therefore, not a group for for it to be a group, inverse should exist for every element of the set, but inverse does not exist for all the elements except for one element. Therefore, sir, it is not a semigroup. No, it is a semigroup. Semigroup but not a monoid. No, it is a monoid. Sir, monoid but not a group. Yes, not a group. It is a monoid. Option C is the correct answer. Option C is the correct answer. Clearly, go past. Sir, let's assume we have S, which is any finite set, and then we define this Fs is a set of all functions on set S. That means if we have a function f belongs to f of s, then f is defined from s to s, because any function f which is present in the set fs will be defined from set s to set s. Why? Because the function, it is a collection of all the functions on set s. So if any function is defined from set S to set itself, that is on set S, then it will be a part of the set Fs. Okay, now please try to understand. Then the set of all functions, on set S, with respect to function composition operation, देखो जो हम बोलते हैं f of g, with respect to function composition operation is what? Now, please, first of all, let us check. Let f is a function which is from S to S, and g is a function which is also from S to S. So when we were discussing the concept of function, I told you that if f1 is a function from S to S and f2 is a function from S to S, then f1 of f2 will also be a function from S to S. So if f is a function from S to S and g is a function from S to S, then f of g will also be a function from S to S, and g of f will also be a function from S to S. Therefore, it will be closed. Take any two functions on set S, the composition will also be from set S to set S itself. Therefore, the set Fs with respect to function composition is closed. That's what we discussed when we were discussing the concept of function composition, right? So, closed. Now we already know that f of g of h is actually f of g of h, that we have already discussed when we were discussing the concept of function, that function composition is associative. Yes, sir. Function composition on functions from set S to set S will be associative. Yes, sir. Now, sir, do we have any, please, if f is a function from S to S, and if I have an identity function on set S, then we know that f of is will be f and is of f will be equals to f. So we have an identity function on set S such that the function composition of f with the identity function on set S will be function f only. So what do we know? That identity is present. Okay, sir, will it be a group also? Please try to understand. All the functions from set S to set S need not be bijective. All the functions on set S need not be bijective. All functions on set S need not be bijective. And inverse will not exist for those functions therefore not a group. Clear? So yes, sir, function composition on the set of all the functions on set S is closed. Function composition associative. Identity function on set S will behave as identity element with respect to a function composition, but inverse will not exist for any function which is not a bijective function. Therefore, again, same story, it will be an algebraic structure, it will be a semigroup, it will be a monoid, but group, no, because inverse does not exist. So again, the same answer, monoid but not a group. Monoid but not a group. Next, fast. Sir, that is the set of all integers. The binary operation asterisk is defined as that if you take two elements A and B, take two elements A and B, then A asterisk B is defined as max of A and B. So what is A asterisk B? A asterisk B nothing but max of B. Now my question is, if A and B are present in the set, if A and B are present in the set, then the maximum of those two will be one of those two elements. Therefore, the result will also be present in the set, because if A and B are already there, so the maximum element will either be A or B, and that element is already in the set. Therefore, it will be closed. Yes, sir. Sir, A and B are what? Sir, A and B are the integers. So Z is the set of all integers. Z is the set of all integers. So if I take the set of all integers, then with respect to this binary operation asterisk, which is defined as max of two element, will it be closed? Yes, sir. Now, if you take three element, in whatever order you perform the operation, let's assume A asterisk B asterisk S or C. So it will ultimately produce what? Sir, it will ultimately produce the element which is the maximum among three, or which is largest among three. So whatever order, first you check the maximum of A and B and then check with C, or first check the maximum of B and C and then compare that maximum element with A. You will in any case the output will be the maximum element out of these three elements. Therefore, it will be associative. Yes or no, sir? In whatever order you check whether which one is largest among 1, 2 and 3, result will always be 3. In whatever order you compare them. Sir, yes sir, it will be associated. Now my question is, do we have identity element? Do we have identity element? Sir, we need the result as the maximum of 2. So, if you want to ensure that whenever we compare the maximum of this question mark with an element A, it should come out as A only for all element A belonging to integer. So, for it to happen, this question mark must be the smallest integer, must be the smallest integer. You may say, sir, it will be minus infinite, but minus infinite does not exist. Minus infinite does not exist. Even if you take minus infinite, then you can subtract minus 1 from it, it will become minus infinite, and this infinite will be smaller than this infinite. This minus infinite, I'll just the minus infinite on the right hand side will be smaller than this minus infinite on the left hand side. So we don't know what is the actual value of the infinite. So minus infinite and plus infinite. So the idea is quite simple, that this question mark must be the smallest integer. So identity element should be the smallest integer the set of all integers. Set of all integers. And it does not exist. Not exist. Therefore, not a monoid. If identity element is not present in the set, then it is not a monoid. Then it is not a monoid. So, sir, this is an algebraic structure, fine, good enough. This is a semigroup, fine, but It is not a monoid. Not a monoid. So not a semigroup, no. So semigroup but not a monoid. Semigroup but not a monoid. Option B will be the right answer for this question. Perhaps the last one. The last question. Last question. Look at this. Sir, let Q asterisk be the set of all positive rational numbers. So they are only positive rational numbers. We are not talking about zero. It is neither positive nor negative. We are not talking about negative rational numbers. Q asterisk in this case is defined as set of all positive rational, right? The binary operation asterisk is defined as, sir, if you take two elements A and B, then the binary operation A asterisk B is defined as multiplication of A divided by 3. Multiplication of A and B divided by 3. So if this is something, let's P by Q is R by S, then the result will be nothing but P by Q R by PR divided by 3QS. PR divided by 3QS. Something like that, right? So the idea is, if you have two elements A and B, the binary operation A asterisk B is defined as AB by 3 for all elements A and B belonging to set of all positive rational numbers, and if it is given that the set of all positive rational numbers with respect to binary operation asterisk, the set of all positive rational numbers with respect to this binary operation asterisk is a group. If it is given that it is a group, then if it is a group, then we know that identity element will be present. Then we know that inverse of every element will be present in the set itself. So what is being asked, if it is a group, then it is asking the identity element of the group. What will be the identity element of the group? So first question is quite simple. We know that let E is the identity element. Let E is the identity element. Now, for any element A belonging to set of all positive rational numbers, A asterisk E will be equals to A only because E is the identity element. Now, how do we define A asterisk? So the binary operation of A and B is defined as AB by 3. Therefore, the binary operation of A and E will be defined as AE by 3. And this AE by 3 is actually equals to A. Now, this A and A will be get cancelled out, and the value of E will come out as 3. Value of E will come out as 3. Therefore, the identity element with respect to binary operation asterisk defined like this will be, now we know the identity. Now the second part is that for any element A belonging, for all A belonging to, for all A belonging to group, what will be inverse of A? So please try to understand. Let, second part, let inverse of A is nothing but A. We know, what do we know? That if we perform the binary operation of element with its inverse, then it will be identity element. We know that the binary operation, so that's what we discussed when we were defining the concept of group. What do we say? Sir, for something to be called a group, inverse should be present for every element of the set. Now, if A and B are inverse of each other, then their binary operation will produce the identity element. So let's assume that the inverse of A is A inverse. Let's assume that the inverse of A is A inverse. Therefore, the binary operation of A and A inverse should produce identity element. Now, what do we know? Sir, A asterisk A inverse is nothing. Sir, A asterisk A inverse is nothing but A into A inverse by 3. And we have already calculated the value of identity element. We know the value of identity element will be 3. Therefore, what will be value of A inverse, 3 3s are 9 by A. The value of A inverse will be 9 by A. The answer for second part will be the answer for first part. So if you know the basic definitions of different type of structures in the group theory, that what do we mean by algebraic structure, what do we mean by semigroup. So algebraic structure set should be closed with respect to binary operation asterisk. We'll think like that. So it should be associative for an algebraic structure to become a semigroup. Similarly, for a semigroup to become monoid, the identity element with respect to binary operation must be present in the set. Now, when exactly the monoid will become a group? A monoid will become a group when for every element of the set, the inverse with respect to binary operation asterisk will also be present in the set for every element. Then it will be called a group. Apart from that, the concept of commutative group will be simple. That for all A and B belonging to the set, the binary operation A asterisk B must be equals to B asterisk. That will be the concept for commutative group or abelian group. So this is it. So this is just the introductory session for the group theory. We'll have 3 more lectures on the concept of group theory. Tomorrow we'll try to understand the concept of finite group. So whatever we discussed is the general concept related to group theory. Tomorrow we'll try to understand the finite groups along with the operations which are defined to create the finite groups of real number. Then we'll try to understand in the upcoming lectures, we'll try to understand the concept of subgroup and cyclic group. So every year, almost every year, a question is asked from the concept of subgroup. So in the last 4-5 years at least, they have asked the questions from the concept of Lagrange's theorem at least 3 times, and that's a very easy concept, that the order of an element of the group will divide the order of the group, and the order of subgroup will divide the order of the original group. So based on this simple definition, they have asked the 3 times in the last 5 years. So we'll try to understand that how exactly the Lagrange's theorem will work in the context of subgroup and in the context of order of element of a group. Anyway, so in today's session, we have understood the concept of algebraic structure, that the set with respect to binary operation asterisk must be closed. The binary operation asterisk should be associative for it to be become semigroup. Monoid if identity element is present. Group if inverse of every element is present in the set. Abelian group if the binary operation asterisk with respect to elements of the set is commutative. So that will be all for this particular session. So in the upcoming session, we will learn more about group theory, but it was just the introductory session. Thank you very much for joining. Keep learning. Have a nice time. Thank you very much. Bye bye.